So this idea of electrostatic force and how similar it is to gravity sort of led to an idea that matter was basically a clump of protons in a nucleus with a bunch of electrons orbiting it like moons, which is close but not quite. But it works for reasonably simple atoms like a hydrogen or a helium. And it has results that are pretty close to reality. So it's a good starting point, certainly about the conversation about how matter is structured. So I'm going to draw for you a nucleus, and inside this nucleus there's going to be some number of protons. So I'm going to use an n for that. So there's some number in there of that basic charge. And then out here, I'm going to put an electron, and I'm going to assume that it is in some sort of orbit, like so. Okay, now if you were to think about how we built Kepler's laws for orbits, the idea was that the centripetal force required to stay on that circular path was provided by the gravitational force of the larger object. Now in this context, we're not talking about gravity anymore. We're talking about the electrostatic attraction between the electron and the positively charged nucleus. So instead of Fg here, I'm going to put Fe for electric. Centripetal force was mass times the speed squared divided by the radius of the orbit. Our electrostatic force, we figured out, was K, Q of the nucleus, Q of the electron, divided by the radius squared. Now the charge of an electron is just the basic charge, and the charge of this nucleus is some number of the basic charge. So I'm going to make a few notations here. I'm going to use Q as 1.6 times 10 to the negative 19. So whenever you see Q going forwards from here, it's that number. That's just a constant. I have an R on this side and an R squared on that side, so that's going to go away. Okay, this is the charge on the nucleus. That's N of these. That's one of these. And I've got an R there. Well, I can shorten that up by calling it Q squared. And I've got to remind myself that this M here, this is the mass of the thing in orbit. Now for those gravity equations, the masses dropped out because you had mass on both sides. Here they do not. So I'm going to have to remind myself that that's the mass of the electron before I go anywhere further. So I'm going to leave that like so. If you think back to the de Broglie wavelength section, where wavelength ended up being Planck's constant divided by the mass multiplied by the speed of the particle in question. If we do that for an electron, we end up with something like this. And we briefly touched on the idea that the orbit around the nucleus of this thing has to be an integer number of wavelengths in order for that electron to positively and or constructively interfere with itself. So this orbit here, the circumference 2 pi r, has to be equal to some number. So I'm going to use a p, some number of the wavelength. Otherwise, the electron doesn't fit quite right, and it starts to interfere with itself. So this circumference here has to be that. My wavelength I can get from here. P H for Planck's constant, and I've got the mass of the electron and the speed of the electron down there. I'm going to arrange this so that I get the speed up top. pH, mass of the electron, over 2 pi r. And I'm going to square this thing so that I can shove it in over here. So v squared would be that number of wavelengths squared, h, over the mass of the electron, sorry, squared because I'm squaring everything, mass of the electron squared, 2 squared is 4, pi squared is pi squared, r squared is r squared. I'm going to take this, and I'm going to combine them. So the mass of the electron multiplied by v squared, which is this thing, p squared h squared, over mass of the electron squared, 4 pi squared r squared, equals knq squared over r. Goodness, this is exhausting. The mass of the electron up here divides out one of the mass of the electrons down there, so that's gone. I have a radius over here, which eliminates one of the radii over here. I'm going to pull this up so that this r comes up to this side. So I have p squared h squared over this k and this n go down here. Mass of the electron, 4 pi squared, equals, my q squared went down there as well. Equals r. I got everything, p squared, h squared, mass of the electron, 4 pi squared, radius came up, mass of the electron, k and q squared are down there. Here we go. So those two conditions together, that the electrostatic force has to be sufficient in order to create a circular orbit, and that that circular orbit has to be some integer number of full wavelengths of the electron, end up giving me an equation for r. So what I've got there is a first stab at the radius of a hydrogen atom, or in fact any atom, based on p, which was the number of wavelengths I'm using, h, which is a constant, k, which is a constant, mass of the electron, which is a constant, 4 pi squared q squared, which are all constants, and this n, which just counted how many protons were in the center. So if I wanted to make this question about lithium, which is the third atom in the periodic table, this would be a 3. And I'd have a relationship between r, so the radius, and p, which is the number of wavelengths. So I'm gonna clean this up a little bit, and I'm gonna write this thing over here so that we can sort of work with it a little bit. Okay, so for hydrogen, let's calculate some of this stuff. So if I'm talking about hydrogen, H is Planck's constant 6.63 times 10 to the negative 34. 4 is just 4, pi is just pi, K is 9 times 10 to the 9. The mass of the electron is 9.11 times 10 to the negative 31 kilograms. The basic charge is 1.6 times 10 to the negative 19 coulombs. And N is the number of protons in the center. So for hydrogen, N equals 1. All the rest of these numbers are constants. They don't change when you change the atom here. Only N changes for the atom. All the rest of this stuff is just constant. So I'm going to do this in 2 steps. First thing, I'm going to put all these numbers into here, and I'm going to reduce them to one single constant so that this is a little less cumbersome to use. So my radius for hydrogen will be this P, which I haven't decided what that is yet. 6.63 times 10 to the negative 34 squared divided by 4 pi squared. K is 9 times 10 to the 9. Mass of the electron is 9.11 times 10 to the negative 31. Q is 1.6 times 10 to the negative 19. I'm going to square that one, and then I have this N down here. So R equals. Okay, here we go. 6.63 times 10 to the negative 34 squared divided by 4 divided by pi squared divided by 9 times 10 to the 9 divided by 9.11 times 10 to the negative 31 divided by 1.6 times 10 to the negative 19 squared gives me 5.305 times 10 to the negative 11. So this number squared divided by this, divided by this, divided by this, divided by this, divided by this squared gives me that number, and I still have some letters left there. I still have a P squared, and I still have an N. So there we go. I've done most of the work for you now. For hydrogen, N is 1. So if I pop that in there, for hydrogen, N equals 1. Therefore, the radius is 5.305 times 10 to the negative 11 multiplied by P squared. So P was the number of full wavelengths that I have wrapped around this particular orbit. So the smallest that P can be is 1. Right? I have 1 full wavelength wrapping around the outside. So the radius of my first orbit is 5.305 times 10 to the negative 11 meters. Okay. Well, how about my second orbital, R2? Well, the second one that would fit would mean that I'd need 2 full wavelengths. So it's longer, which means it's going to have to sit out here. So this one was 1 wavelength. This is 2 wavelengths. So I'm going to take that 2 and I'm going to park it in here. 5.305 times 10 to the negative 11. 2 squared is 4. So that number times 4 gives me 2.121. 2.122 if I round to the negative 10 meters. Okay, so I'm going to write that number up here, because I'm going to need it in a minute. I'm going to write this number up here. I'm going to clear this off, and we're going to do a little bit of thinking about what's happening between these two orbitals. Okay, so if I have an electron orbiting at this location, it's going to have a speed. And it's going to have, so that means it has kinetic energy, and it's going to have an amount of electrostatic energy owed to that particular proton. So I'm going to have to work out those two things. So first off, the electrostatic energy would be K Q1 Q2 over R squared. So at this particular radius, that would be 9 times 10 to the 9 times the charge of the electron times the charge of the proton at the center divided by this radius. And because it's energy, it's not squared. Alright, so let's give that a try. 9 times 10 to the 9 times 1.6 times 10 to the negative 19 squared gives me 2.304 times 10 to the negative 28 divided by 5.305 times 10 to the negative 11. So that's 4.343 times 10 to the negative 18. Now I'm going to be a little sticky about the energies here. One of these is the charge of the electron, so that should be negative. So there's that much energy owing between those two things. Okay, lovely. So if we're going to try and get the kinetic energy, I need to have the speed. And we did that by taking centripetal force, V squared over R, and making it equal to the electrostatic force. So the speed squared would be an R and an R divided on that side would be K Q1 Q2 divided by the mass of the electron and the radius of the orbit. Okay, so the speed squared at this particular orbit would be 9 times 10 to the 9 times the charge of the electron times the charge of the proton divided by the mass of the electron and its radius, which is here, 5.305 times 10 to the negative 11. Radius of the orbit, I should say, to be more clear. So speed squared for this particular electron would be 9 times 10 to the 9 multiplied by 1.6 times 10 to the negative 19 squared gives me that same number that keeps coming out, divided by 9.11 times 10 to the negative 31 divided by 5.305 times 10 to the negative 11, which gives me 4.767 times 10 to the 12. Now that's the speed squared. So my speed then would be the square root of that, which gives me 2.183 times 10 to the 6 meters per second. So that's less than 1% of the speed of light, which is encouraging because if I were going too fast, if I were getting close to the speed of light, I would have to replace this mass of the electron with gamma mass of the electron in order to get its relativistic mass. Fortunately, we don't have to worry about that. So here's my speed. But I can work out the kinetic energy now. Be 1/2 the mass of the electron multiplied by its speed squared, which I have here. So the kinetic energy then, re-square that, divide by 2 times 9.11 times 10 to the negative 31 gives me 2.172 times 10 to the negative 18 joules. And this was joules as well. Notice that these are on the same order of magnitude. That's encouraging. So my total then would be the kinetic energy plus this energy tied up from electrostatic potential. So if I take my 2.172 times 10 to the negative 18 and I add negative 4.34 times 10 to the negative 18, I end up with negative 2.168 times 10 to the negative 18 joules net. Okay, this is at that radius. Okay, now I could do this calculation again here, but it's going to end up on my face. So I'm just going to erase some of this stuff so I can record this amount of energy here, and then I'm going to do the same calculation but using that radius over here. So let me do the first one before I erase it. Notice that the energy for the electrostatic then will be this process, but instead of using the first radius, I'm using the radius of the second orbital. So it will be 9 times 10 to the 9 times 1.6 times 10 to the negative 19 squared. And instead of dividing by this radius, I'm going to divide by this orbital radius. It's 2.122 times 10 to the negative 10, which gives me 1.086 times 10 to the negative 18 joules. Okay, and it'll be negative because I'm stuck in an orbital well. Notice that this number is closer to 0 than that one is. It means you had to dump a considerable amount of energy into this system in order to drag that electron further away from the proton, which is exactly how gravitational energy worked. We could do a lift calculation, if you like, to find out how much energy it takes to get from here to here, which is just a difference, this minus that. But I can't really discount this kinetic energy part here, so I'm going to work that out as well. So my speed squared at that radius would be, all of these numbers are the same, except I'm dividing by my new radius instead of 5.305. So 9 times 10 to the 9 times 1.6 times 10 to the negative 19 squared divided by 9.11 times 10 to the negative 31 is, so that's all this garbage. And instead of 5.305, I'm using my new orbital radius divided by 2.122 times 10 to the negative 10. My b squared will be 1.192 times 10 to the 12, which is smaller than that one. So speed would be square root that. Gives me 1.092 times 10 to the 6. Yep. Okay, so it's going about half as fast as it was before. Now that should make sense, because if it's going 2 full wavelengths instead of 1 full wavelength, that means it's going twice as far in the same amount of time, so it should be going twice as fast in order to get that pulled off. No, it didn't quite work out, but there's a proportionality in there for doubling. You think about it, maybe you can figure it out. Okay, good. So, where am I at? I need my kinetic energy then. So I'm going to take that speed and I'm going to square it, cut it in half, multiply it by the mass of the electron, and I get 5.429 times 10 to the negative 19 joules. Okay? So I can get a total then. This energy plus that energy, so 5.4288 add negative 1.086 times 10 to the negative 18 gives me negative 5.431 times 10 to the negative 19 joules. Okay. Lovely. So keeping in mind that these numbers are approaching 0, there's less energy tied up than there is in this one, because this number is closer to 0 than that one is. Which means that in order to get closer to 0, you had to dump energy in. Okay. Well, now that we have the net energies, I'm going to erase this because that was our sort of transcript for how to do it. I'm just going to record the critical numbers. E is negative 4.343 times 10 to the negative 18. Don't need that anymore. Speed 2.183 times 10 to the 6. And E total is negative 2.168 times 10 to the negative 18. Okay, so here's where things get neat. According to the de Broglie wavelength, this orbit works because the electron fits on this circle. And this one also works because the electron fits on there twice. But no space in between them works. So you can't have an orbit that's halfway between those two things because you don't have an integer number of wavelengths for the electron and you start to get destructive interference. So the electron is either here on this path or it's here on this path. So let's start it on the outer one. Let's start it with this amount of energy. And then for some reason, that electron decides that it's going to change tracks to this lower one, right? That has a different energy value. So how much has the energy changed? Well, delta E is the E at the end, subtract the E at the start. That's just how you do a delta. So if the energy at the end is the energy on this path, that would be this number. 10 to the negative 18. And the energy at the start would be this one. 1 times 10 to the negative 19. So my total energy then, or my change in energy, would be this thing. Subtract negative, it's like adding. And I get negative 1.625 times 10 to the negative 18 joules. Okay. So if my electron starts here and it decides to transfer to this new path, it has to shed precisely that much energy. It can't shed close to that, it can't shed a little more, can't shed a little less. It has to shed exactly that because it's only allowed to travel on these very precisely defined tracks. So exactly this amount of energy must depart this system. So how does it do it? Well, these electrons, as they switch locations, are changing the local electric field. So what it ends up doing is generating a photon. It generates a little chunk of light that leaves the system Now, if it does that, right, photons had particular things about them, right? Like the energy of a photon was this. So if a photon of that much energy, 1.625 times 10 to the negative 18, it's negative, by the way, because energy has to leave the system in order to make this happen. H is 6.63 times 10 to the negative 34. There's an F. So the frequency of that photon times 10 to the negative 18 divided by 6.63 times 10 to the negative 34. Let's see. Divided by 6.63 times 10 to the negative 34 gives me 2.45 times 10 to the 15. Hertz. And if I have a frequency, I can get the wavelength of that particular photon using the universal wave equation. So I just have to take the speed of light divided by that number. So put that in the denominator times the speed of light gives me 1.224 times 10 to the negative 7, which is 122.4 nanometers. Okay. That's a very specific answer. And so what you've got here, this is sort of the beginning of quantum mechanics, is that because the electron can only be in this track or this track, there's a very specific amount of energy that has to be transferred either out of the system or into the system in order to make those electrons jump. And if you figure out that energy and you feed it from photons, then there is a very particular frequency / wavelength that makes that work. And these things, the frequency and the wavelength of light, are related to what we would call color. Right? This is a color. So when you excite hydrogen and then allow the electron to drop back down to its resting state, which is the shortest one, it will emit a particular color. And if you shine light into hydrogen, or you try to excite hydrogen by shining photons on it, it will absorb a particular color as those electrons jump. So if you're looking at a planet that's about to transit the sun, and you can get the light as it just clips the atmosphere, if you look at the light coming from that particular planet, and you look at the colors that are contained in that light, if you have a hole at this particular color, then you've discovered that the atmosphere of that planet is absorbing at hydrogen's first spectral line, right? It's this first energetic orbit. And so if you can find those holes, you can use them to identify gases that light is passing through. So if you've ever wondered how anybody ever told you that the clouds of Venus contain sulfuric acid, but no one had ever been there, well, this is how, as Venus approaches the sun, light gets bent through its atmosphere, and you can take the light coming through and you can analyze it for which colors are coming and which colors are not. And because there are certain absorption lines for hydrogen, there are certain absorption lines for helium, for lithium, for beryllium, for all of those atoms. If you remember, this radius came from an equation that contained the number of protons inside that atom. You can get a count of what percentage of the atmosphere is boron, and which percentage of the atmosphere is oxygen. It's really neat, and you don't have to be there. That information is contained in the light that skims the atmosphere of that planet. This little technique has been used for analyzing organic samples as well on Earth, right? You take something and you burn it, or you ionize it with a quick jolt of electricity, and then you look at the colors that come out. It's called spectrometry. And if you look at those colors, it will tell you which atoms are contained in this mysterious substance that's sitting in front of you, which is sort of cool. So the problem sets are going to ask you to do this question. It's going to give you a nucleus with a certain number of charges, and it's going to ask you to find the first few radii of those that are allowed based on the de Broglie wavelength, and it's going to ask you for the amount of energy it would take to jump from one level to the next. So you can use this one as an example. This was hydrogen. So good luck.